This is Ananyaa,
My name's Sydney.
And my name is Elliot.
and this is our pitch on permanent magnet motors versus induction motors. Firstly, to introduce our issue, alternating current motors are currently favored in the industry due to their high efficiency, superior power density, and reduced energy consumption. Implementing these AC motors in electrical vehicles would result in more powerful and very efficient cars. But which ones do we use? In our pitch, we are conducting a deep console study on induction and permanent magnet motors to determine with your investment which one is the best and how we can use your investment to further improve our models and softwares to better electric cars in the future. Now, looking at some initial research that we conducted.
Input power. Both the types of motors that we modeled in this project have input power based on the current and voltage. Three-phase motors, like the induction motor we used, have a square root 3 coefficient in their power formulas due to the three currents, with each phase shifted by 120 degrees. Single-phase motors, on the other hand, such as the permanent magnet motor used, do not have any such coefficient.
Looking at output power, the output power is calculated by subtracting all power losses from the system from the inputted power. In induction motors, after the power is supplied to the stator, the motor experiences losses in power. Power is then transported to the rotor, and this is the power that is then converted into mechanical power. In this COMSOL model, the output power is calculated by using the equation power is equal to axial torque times the angular frequency of the rotor. In permanent magnet motors, they are not subjected to as many losses because they do not need constant current flowing through them to create a magnetic field. In this COMSOL model, the output power is purely mechanical from the rotor.
Efficiency. Efficiency in an electric motor is the ratio of mechanical power output to electrical power input. According to our research, induction motors typically achieve maximum efficiencies around 90%, with this efficiency dropping significantly when partial or non-existent loads are applied in place of the normal load. Permanent magnet motors, on the other hand, can typically reach maximum efficiencies of 97.5%, regardless of the load applied.
Looking at losses, any energy that does not directly contribute to mechanical work is considered lost in the system. In induction motors, there are two types of losses. There are fixed losses, which remain constant during the normal operation, and there are variable losses, which change with the load and depend on the current in the stator and the rotor windings. In permanent magnet motors, these motors utilize magnets and have relatively no rotor losses. They are able to experience eddy current losses in the magnets and also can experience demagnetization and core losses over time.
Now, looking specifically on the permanent magnet motors, our model is an AC permanent magnet motor that rotates by quickly switching induced magnetic fields from positive to zero to negative and back to zero. Each permanent magnet is orientated to either have a positive or a negative pole by facing outwards and alternating between the poles. This creates a push-pull effect, which then creates the induced magnetic field that we're hoping for.
The physics applied to the permanent magnet motor model fall into the following two modules. Moving mesh, which allows parts of the motor to physically move in the simulation where they otherwise would not, and defines its angle as a function of time and angular velocity, and rotating machinery magnetic, which governs why the motor moves, modeling the magnetic fields, magnets, and currents, dictating how they affect the motor. Furthermore, the model is split into 18 nodes for the sake of computational simplicity, which is why this part shown is 1/18 of the total ring.
Now, looking to the results we were hoping for, we first looked at input and output power. Looking at input power, it has two different parts. Firstly, looking to the coils, we see a purely sinusoidal wave. This is because the power from the coils is proportional to the current squared, which is an AC current, meaning it changes over time, with this peaks being around 9 watts per hour. Now, looking at the total input power, we have to include the mechanical power, which creates this weird shape that we're seeing. This is due to the COMSOL's inefficiency to be able to fully compute mechanical power due to there being errors in the rotational physics that are being applied. However, we see that the total input power has peaks around 55 watts. Looking at output power, as previously mentioned, output power is purely mechanical, coming from the spin of the rotors. And we see peaks of around 45 watts, showing that there is Looking at efficiency, we can see that the efficiency bounces around due to the changes of the current and peaks in the powers that we saw. Looking into the efficiency overall, we see that the trend line shows an efficiency of around 85 to 87%. Looking at the losses, there are two different losses coming from the loss of the magnets and the loss of the coils. We can see that the coils produce the most amount of loss, attributing to the total loss that we see in the red graph shown, showing that it does change over time due to the AC current applied. Now, looking at the induction motors, we have a two-pole, three-phase induction motor model. Essentially, the induction motor rotates due to the electromagnetic induction. Alternating current flows through the stator windings and it creates a magnetic field. This magnetic field induces currents in the rotor, causing it to generate its own magnetic field.
So the physics applied to this induction motor would be magnetic fields. So since it's a three-phase motor, there are three separate phase physics that are applied to this, just to ensure that the coils that are meant to be grouped together are in fact grouped together. There's also magnetic insulation, which separates the core of the motor from the outside of it. This just prevents any energy loss since the magnetic flux is not able to leak into neighboring domains. This prevents unwanted eddy currents forming from the surrounding metal. There's also free space in between the rotor and the stator. This is just so the rotor is actually able to rotate. This free space is filled with air to allow for the magnetic field to cross over, which creates a torque in the rotor. And then finally, there is a force calculation on the rotor, and this is needed just because of the air gap in between the rotor and the stator. This force acts on the rotor caused by the magnetic field, which in turn adds a torque. And then looking at the input and output power, the motor behavior depends on the rotor speed, slip, and load. And so this plot, the input power, shows the coil power versus the rotor speed. This shows how much electrical energy the motor needs at each speed. This plot is generated by using the equation P equals IV for each of the three-phase coils and adding them together. The output power graph is the mechanical power versus speed, and this shows how useful the motor is during operation. The peak on the graph is the maximum mechanical power outputted from the motor. This shows up at what speed the motor should run at for its best performance, and the output power is calculated by multiplying the mechanical torque by the angular frequency. Looking at efficiency and losses, a high efficiency means that there's less waste and it is actually cheaper to run the motor. This efficiency graph shows that there's a maximum efficiency of 6% during the operation of the induction motor. As stated earlier, the efficiency would increase when a load is applied to the system, which we did not model. We are just showing the operation of the induction motor on its own. And then looking at losses, the graph just represents how much power is lost. So as the angular speed of the motor increases, so does the lost power. This relationship, however, is not linear. As you can see, the motor starts off with a sharp increase in losses before leveling out just below the 650 watt area and then steadily increasing from there.
Conclusions. Industry applications. There are many different types of motors, and each has unique properties and advantages over others. Motors are an extremely widely used item across multiple industries, and thus the industry applications of optimizing motor design are equally vast and include but are not limited to electric vehicles, as well as all motorized vehicles, electricity generation through optimizing turbine and generator design, industrial machinery, and much, much more. By optimizing power intake and efficiency of these devices, the goods and services which they contribute to providing will become significantly more accessible and productive. Our findings. The induction motor had a significantly lower efficiency without a load, maximizing at 6%. Furthermore, its reliance on three synchronized currents creates additional potential places for failure to occur. The permanent magnet motor, on the other hand, had significantly higher efficiency when modeled without a load, never dipping below 77% and averaging approximately 86% efficiency. Furthermore, its simplistic current requirements put it clearly above the induction motor in terms of superiority in this modeling experiment. Finally, according to our research, the permanent magnet motor is expected to still have a higher efficiency when loads are applied. Overall, we are recommending that the permanent magnet motor be the optimal motor of these two to be used in the electrical vehicles industry, since its efficiency both with and without loads is significantly higher than that of the induction motor. Next steps. So far in this project, our group has been able to compare and contrast two types of motors to yield conclusions about their advantages and the more effective of the two designs. With more funding, this research could be expanded to include many different types of motors, discovering and optimizing their unique advantages and strengths, as well as diving deeper into the motors than we are currently able to. With these conclusions, we would be able to determine the optimal situations and ways in which to use each distinct design of motor, as well as potentially creating a new, more generally optimal design with our findings about what makes them most optimal. We are asking for a total investment of $50,000 across the next 12 months, with a meeting with a review board at the 6 and 12-month points to look over the work and determine if additional funding is warranted. This funding would allow us to continue and expand our research in the ways described previously, and this research could reveal unique optimizations in motor design which could be utilized by industry. Thank you so much for listening. We hope you enjoyed our presentation, and we hope you will consider funding our research. These are our references. Furthermore, we use AI to help understand and navigate Console.